thanks very much for the introduction. I'm delighted to be here. Normally, I'm in San Jose for a very different reason. Usually it's for various photonics and optics conferences that I attend. My training is in quantum photonics. We spend a lot of time talking about quantum technology, the really low-level stuff, but a kind of a shockingly low amount of time talking about the applications of that technology. So it's very gratifying and kind of a dream come true that this kind of conference exists and we can really talk about the applications at an enterprise level. So let me begin. I'm going to give you an overview of what I'll speak about today. So I'm going to start with a bit of background information on the company. We've kept a low profile, I think, for the past couple of years, but we've made enough progress recently that we'd really like to share that with all of you. So we'll give you some background there. Then I'm going to dive into the technology and tell you about photonics and why we think it's one of the most promising, if not the most promising platform for both the Holy Grail, right, the full fault-tolerant universal quantum computation platform that everyone is seeking and that we're all working towards, and we've heard a lot about today. But maybe even more exciting for me are the near-term applications and the near-term problems that we can solve with the photonic approach. So that near-term architecture will get me sort of deeper into the technology, and I'll introduce this idea of Gaussian boson sampling, an architecture that I think probably many are not familiar with, but has some very exciting promise for realizing very near-term problems and which have enterprise applications right away. Then I'll talk about those applications, talk about what sectors, and I'm going to finish up at the end with a discussion of what products we have to offer. We're very much a customer-focused and product-focused company, and we're finally at the stage where we can offer those to customers. Okay, so this is a bit of a divisive session. It's a hardware session. We've got kind of three different platforms being pitched: trapped ion, superconducting, and photonics. So certainly there's a lot of disagreement in the room, as there should be. But I think there's probably one thing that everyone can agree on here, and that's if you're going to build any kind of quantum computer, if you're really going to tackle this challenge, you need an incredible team. And we spent a couple of years building an incredible team. We're over 50 people now full-time. These are staff mostly based in our office and labs in downtown Toronto, right in the core. Disciplines are diverse, but the usual kind of physics, engineering, computer science, the relevant backgrounds, majority PhDs in those related disciplines, academic pedigrees from all the best institutions around the world. In terms of our funding timeline, we've raised $41 million to date, majority of that from a Series A, which we closed over the summer of this year of 2019. And just kind of looking at this on the big screen, the alignment between those sort of headshots and tabs is not supposed to be so literal. Raf, he's in the audience, he doesn't really have $41 million to his name. I don't have 35 PhDs. Maybe Christian has 50 people, I guess that's true. But so, if we've got a really great team, what are we actually doing? What's that team actually doing? And the answer is that we're building a full stack quantum computing platform based on photonics. So full stack really does mean full stack. We have everything from the hardware. This is the chips. I have one here. If you're interested in taking a closer view, come to our booth in the ballroom. So that's the chips. We do all of our own design, and that's based on silicon photonics. Maybe some variants of silicon photonics that are maybe a little less well known, but still within that overall umbrella. All the way up to the user interface. These are our software offerings, Strawberry Fields and Penny Lane. Strawberry Fields is our sort of API, how you program our quantum computer. It can also run on a simulator, and it's the way our hardware is accessed. We also have Penny Lane. Penny Lane is maybe the premier quantum machine learning library, and that one can both access our hardware, but it plugs into all the other providers as well. So it's very useful for training quantum computers. It's kind of like the TensorFlow or the PyTorch for quantum computing. And everything in between means our cloud access model. We can deploy these systems for general use by the sort of the model that everyone else is taking for cloud access, and the applications layer, which is an API. If you want to program our computer directly, you can certainly do that. You can operate at the lowest level. Or if you just want to have nice, well-wrapped Python function calls, you can do that too, and that's the applications layer. Stay tuned. I think we should have very soon a paper coming out on describing that applications layer. A lot of hard work from the software and algorithms team. So, maybe the most, diving into the technology, maybe the most common question I get when we're pitching photonics, trying to convince people that photonics is so great. Well, if it's so great, how come more people aren't doing it, right? How come the Googles and the IBMs, obviously very smart people, when they were placing their bets on a hardware platform, if they want to get into quantum computation, why didn't they choose photonics? And the truth is, at the time when those bets were being placed, I think photonics would have been the wrong choice. So in other words, the timing was not right. Photonics was not ready for prime time, but it is now. And the factors that sort of drove that are threefold. We kind of split them into three categories. Number one is advances in photonic chip fabrication. This is something that even in the past 2 years, there have been leaps and bounds made by taking the technology used for microcircuits, integrated circuits, the kind of conventional CMOS type technology, adapting it to photonics, and now the level of performance that you can achieve in key metrics like optical loss and the various imperfections you have to minimize of the sort of photolithographic process that we use to make these chips has advanced to the point where it's now ready, can meet the very stringent demands. As Chad did certainly a good job motivating it. Whatever you're doing, any kind of chips, they have to be, you need materials research, you need the really, really lowest level kind of stuff. And photonics is no exception, but it's now ready. You can actually commercially access these things, these kind of platforms in some cases through foundries. The barrier to entry is not exactly low, but it's something that a startup ourselves can actually bite off. Advances in optical to telecom technology is number 2. What I refer to that's kind of equivalent to saying that we don't need to invent a lot of our own tools. We're very lucky in optics and photonics. We have a nice synergy with an industry which has already had billions invested in it and is very much profit-bearing, and this is optical telecom, the fiber optics that bring internet to your office or your home. They've produced things like amazing lasers, fiber components, and other optical components. So that means that apart from the chips and the software and the overall architectural research that we have to do, apart from that, the kind of control systems that go into operating our system, into testing and prototyping, that already exists. And I think that's going to be a crucial factor. It's going to take a while, right? Quantum computing is something, as Chad rightly said, we need to be in here for the long haul, for the long term. And so the more we can borrow from an industry, we need another industry that's already has billions poured into it for an already proven purpose, like telecom, that will motivate that will keep us going and give us the tools that we need. So I think that's been a big factor, especially in allowing us to move very quickly. We've only been around for a few years, and we've already achieved some, I think, fairly remarkable things. The third point that I'd like to highlight is breakthroughs in architectural scaling. What this means, this is referring to both sort of some academic demonstrations in both experiment and in theory. These are proposals that have, in many cases, been demonstrated to get to a million plus qubits using a photonic approach. This is something that's quite unique. You can use quantum multiplexing, so taking a single physical channel and embedding a lot of quantum information. You can kind of think of this like breaking the scaling relationship between the number of qubits you want to operate on and the actual physical size. Photons fly, they're kind of ephemeral, they're bosons. You can create them and you can destroy them very, very easily. And that allows you to multiplex, and that allows you to get to a kind of unprecedented level of scaling, which really is unique to only photonics. So I still haven't told you what's the point. I mean, if photonics is ready, obviously I like photonics, that's my training, motivated maybe back in the day more by the tools. But what's the actual value proposition? Why would you do photonics? Even if it's ready, there's not necessarily a good reason to do it. So this is the value proposition as a hardware platform of photonics for quantum computation. And we split this into kind of 3 different tiles, 3 different axes. The accessibility. Photonics is room temperature compatible. That means that you can do your computation, that chip, right? This chip over here, this operates at room temperature. It's actually online right now, executing jobs in our labs back in Toronto. So it's room temperature compatible, which makes it much more deployable in the long term in kind of edge computing cases. The other one is scalability. I mentioned these architectural breakthroughs. So photonics maybe has the most validated architecture of any of the other approaches in order to get to these million plus sort of mark that you're going to need as you start to deal with the overheads involved in quantum error correction and also to get more data into the system. Another big one is networking. It's kind of a bit of an unsolved problem for a lot of the other approaches. Even if you have 2 quantum computers sitting next to each other in the same room, coherently exchanging quantum information, networking quantum computers can't really be done very well. But for photonics, that's as easy as linking our 2 chips by an optical fiber. Again, the same optical fiber that brings internet into your office. The versatility. So maybe, from the user perspective, you still don't care about those 2 things. You probably care about is the bottom tile. And this is the really unique set of applications that are available to a photonic approach, and our approach in particular, and really quite exclusive to our approach and due to a difference of encoding that we use. It's called the continuous variable encoding. It's encoding information in continuous degrees of freedom as opposed to discrete variables. So rather than 0 and 1, right, this kind of binary quantum computing, we have continuous variables. And that allows us to access a completely unique and distinct set of use cases in the near term without deviating from our path toward universal fault-tolerant quantum computation, the holy grail for everyone, and is really not accessible to the other approaches as they are more qubit-based and not based on our kind of qubit. Our kind of qubit is called a Q mode. Sometimes we interchangeably say, for just to avoid confusion, qubit and Q mode. If I say qubit, I mean Q mode. It's kind of a generalization of a qubit. Okay, so what are these near-term problems? To explain these near-term problems, I have to explain our near-term architecture. So we've done a very block level, very high level schematic of kind of the chip that I was holding in my hand there. This is what it looks like if an artist produces it. This chip is sort of, it's the box bounded here in green. What this consists of is the job of the chip is to take a classical resource, which is a laser, a sequence of laser pulses, conventional laser pulses, and turn that into a programmable multi-system entangled state. And that's what this chip does. How it does that is it has a layer of squeezers. These are gates which sort of you start the quantum state in vacuum, in the ground state, and these squeezers pop out photons in a very special mode, a very special state called a squeeze state of light. Squeeze state of light is our version of our sort of qubit as a fundamental resource. Is this the initialization step? It's a non-classical state of light. And a nice feature of this non-classical state, squeeze states, is if you start to coherently interfere them together, if you mix them, the output is entangled. So these blocks on that diagram are our gates. So followed by the initialization step, you now have a series of gates. This is an optical interferometer, and it's programmable. That's where the user's data enters the chip, and after it goes off chip for detection, for readout, using photon number resolving detectors, photon counting. And then, of course, there might be some post-processing, depending on the application. You probably will have to do some other classical stuff on the side. And a key point to keep in mind, in the most general case, that is to say, if you wanted to fully simulate all instances of a Gaussian boson sampling, this is our architecture, that actually would require exponential time with classical computers. So it is in sort of this domain where supremacy is in principle reachable. And a lot of people are probably familiar, in terms of the name, just a bit of nomenclature here, with boson sampling. Boson sampling has been around for a proposal for a long time, Aronson and Arkhipov. It's maybe thought of originally as this architecture that's maybe more for academic interest, a way to show supremacy, maybe not with useful applications. Gaussian boson sampling is a significant generalization of that. So the types of problems that Gaussian boson sampling can solve is a superset of that. It includes boson sampling, but it's much more general. And the real difference there is that we use these continuous variables. We use squeeze states at the input, and also sometimes some other features called displacements. And that really expands the space. It lets you get well outside of the problem space of boson sampling, conventional boson sampling, and address these interesting problems that I'll tell you about. So to situate that a bit better in the context of the greater field, because this is, I think, a really new architecture. I'm imagining a lot of people, both on the research side and probably on the customer side, are not familiar with it. This is how we view ourselves in the greater kind of terrain of the different approaches that you're hearing about today. We've kind of illustrated this by two roads, and they're converging to the same place. This treasure, this holy grail of universal fault-tolerant quantum computing. Our device is this chip, a high-performance version of it, is actually a synthesizer for the types of states that you need for universal and fault-tolerant quantum computation in the Photonic platform. Along the way, we pick up these applications of Gaussian boson sampling. These are ones that don't require that kind of error correction. They're our NISQ device. A little later on, we'll get optical quantum neural networks. I won't speak too much about that today, but that's get me offline if you'd like to hear more. And then, of course, the other approaches, the qubit-based trapped ions, superconducting qubits and spins and so on, they'll pick up their respective applications. You heard a lot about QAOA and VQE, also very interesting use cases. But the kind of what we're trying to illustrate here is that these are very much distinct, even in principle. If you had a very high-performance ordinary, conventional qubit-based machine, you could not simulate, you could not do Gaussian boson sampling. It's just mathematically, there's no equivalence there. So, enough teasing. What are those problems? Dense subgraphs. So these are roughly speaking, if you can phrase your problem as a graph problem, if you can take your data and structure it as a graph meaning you have a bunch of different independent nodes, you have edges connecting them, and those edges have weights, and you want to ask difficult questions. Questions like, what is the most tightly connected subcluster? That's the dense subgraph graph problem. Max Clique, if you want to find maximally collected, complete subgraphs within the graph, you can embed that in our chip, in this architecture, and solve that problem, or accelerate the solution to that problem. Point processes, generating points in sort of complex distributions. Graph similarity. A Gaussian boson sampler allows you to take two graphs and define a quantum-enhanced metric on whether those graphs are different, which allows you to attack graph isomorphism. This is something very interesting in network theory. Vibronic spectra, we have chemical applications. If you want to simulate something to do with the vibrational modes, the bosonic modes of molecular chemistry, that's better done on a machine that uses photons, which are bosons. There's a much more natural mapping, not for electronic structure, but for the vibrational structure. So vibronic spectrum is maybe a flagship application. Quantum advanced features. This is sort of getting into how you could use GBS as a primitive in machine learning as well. So these are the problems. I won't call them applications. I'm going to get to that. These are the problems that GBS can be embedded in, or into which can be embedded. That was a lot of information. So I'll take just a pause to summarize. Graphs can be encoded in a GBS, in a Gaussian boson sampling device. So it's wider than that, but for the sort of, the people here looking for ways to map their computational bottlenecks onto current day quantum hardware, if your data can be phrased as a graphic, if your question can be phrased as a graph problem, there's a very high likelihood that GBS can tell you something interesting about it. It's a key enabler to universal fault-tolerant quantum computing. That's key. That means that we're not deviating from this path toward universality and fault tolerance, in that a high-performance version of that chip, of our architecture, high-performance GBS chip, actually is a synthesizer for these states that you need for fault tolerance and for universal QC. It's a unique set, it gives you a unique set of applications. These are these problems that you can fit and the applications they address in GBS. And if you'll permit just a little bit of flex, Xanadu really, we spent a lot of time researching these problems, both obviously on the hardware side, but on the applications and software side too. So we really are the world leader in among those groups studying these problems and how to build the computers that solve them. So now we're getting even more to the point. Where do we see this having an impact? So those were problems. That was the hardware. Those were the problems. What are the applications of those problems? We look at 4 different sectors, primarily: finance and banking, chemistry, logistics, and machine learning. Finance and banking, portfolio optimization is a very promising field where this can be applied, and that can be used for new methods to do fraud detection. In chemistry, I mentioned vibronic spectrum. There's also molecular similarity. I can take 2 molecules, represent them as graphs, and try to study whether they're different. This is an important problem in molecular chemistry, and one that's in general quite hard, and that can lead to advances in material design. Logistics, it's not hard to imagine how network optimization, route optimization can be phrased as graph problems. And in machine learning, as I mentioned, you can think of these GBS devices as primitives that can help in model optimization, and that could have an impact in helping autonomous vehicles navigate and kind of the routing problems there. So these 4 sectors are where we really focus our attention. When the rubber hits the road, everyone wants to know, where are we actually in terms of hardware? What have we built and what are we going to build? This is our progress. This is a summary slide of kind of 2019. Where we've been now taking this chip level, this sort of die-scale experimentation, and we now have a fully operating quantum computer, and this is the progress toward that and beyond. So currently, we have chips that operate on 12 Q modes, our version of a qubit. These bars represent our qubit count, and then the line is the gate depth that we've gone to, the number of sequential gates that we've demonstrated and we can operate. So that's 12. We also have chips operating on gate depth around 26. And we're roughly doubling every 6 months on the qubit count, or the Q mode count. So we'll be getting to around 24 mid next year without any architectural overhauls. These are fabrication, tape outs that are already underway. And we project end of 2020, early 2021 to be in the 50+ zone. And that's a very considerable amount of data, and very complex graphs can be studied with a machine of that size. So we're progressing very, very quickly. In terms of the machine that's online running right now, in our lab. I was actually submitting jobs to it just yesterday, sitting in our booth in the ballroom. That's an 8-qubit machine, and we'll be sort of going live outside of internal testing and more limited private demos with probably around the 12 mark. That's our lab. We're very proud of it. It's right downtown in Toronto. You can see, I think that maybe the unique feature, what pops out, is the view. I think we're probably the only quantum computing lab that can claim to have such a nice view of a downtown metropolitan skyline. You can see Lake Ontario out there on the south side. The sunset is beautiful if we haven't drawn the blinds, and you can see some of our hardware team very hard at work there. Actually, behind the gentleman on the left, that black box, that rack, is our quantum computer, and that's the one that's currently running today, serving jobs. And we're very proud of it. You can see also sort of on the west side there, sitting on the edge of the world. You have a great view of the western part of Toronto there on that side of the lab. Very proud of this. And this actually reflects really only 6 to 9 months of progress. This didn't exist in March. We moved to a new building. We had a lab before. Now we're in this kind of upper floor of a building downtown, and it's quite an exhilarating place to work. Okay, now I'm going to shift gears. That was our hardware, that was our near-term architecture, that's our sort of roadmap for scaling how many qubits. I'm now going to shift to another product that we have rolling out, which is kind of falls in the class of professional services. This is our quantum readiness program. I'm going to start by describing a project that's completed. It's one of the ones that I'm able to talk about publicly. This is an engagement we had with 2 global banks, very large, Scotiabank and BMO. A 6-month project, and the objective there was to evaluate the impact of quantum computing on financial derivatives pricing, and the stakeholders there were executives in those banks. Kind of the process worked was we researched the cutting edge techniques, both classical and quantum, for doing this financial derivatives pricing problem, developed a POC, a quantum algorithm, benchmarked it, we simulated it using Xanadu software, and then we benchmarked how that speed up and accuracy worked against the best available classical methods. the results were positive. From this testimonial, they were very happy, and this is leading to follow-ups as well. We developed a proprietary quantum Monte Carlo algorithm for pricing these derivatives, and illustrated a speed up when the corresponding hardware would be available. The speed up would be from hours to minutes. You can really start imagining doing this problem in real time, which would be a game changer in this particular sector of finance, where you don't have to wait to do these things overnight. You can do them as the market moves. So this is our quantum readiness program. It's offered in collaboration with Amazon Quantum Solution Lab, which we're very, very happy to announce. This works on a cycle of knowledge transfer, so we'll engage with you, we'll engage with enterprises, we'll kind of educate you on what quantum computing is, the different approaches, not only ours, but the whole field, and you'll educate us on your computational bottlenecks. We'll train your user. If you have an innovation team or a quantum team that's getting into this, we'll train you on our software and how to access different hardware platforms, both using Penny Lane, which accesses all the different hardware providers, and Strawberry Fields, which is Photonic, for photonic quantum computing. Define a problem, we'll ask a good quantum question, and then we'll try to develop a POC, provide a good quantum answer. So that's actually where I'm going to leave it today. We're going to finish with our products. This is a summary of what we currently have available, and as I mentioned, we're very much a product-focused, very application-focused group of people and company. Xanadu Cloud. So our product this is available in early 2020. You know, it's probably available sooner for sort of select demos, so you can come talk to us. This hardware is running. It is online in a rack-mounted, room temperature operating device. You can submit jobs to it using Strawberry Fields, and we're going to be launching with that in the early part of next year, just as we complete sort of the beta testing. We have our software suite that's available right now. These are open source packages you can use, and again, Penny Lane is for quantum machine learning. Strawberry Fields is really the only software suite for programming photonic quantum computers, especially those that are based on continuous variables. And then our professional services side, we've got the quantum readiness program, and that's about knowledge transfer, user training, asking good quantum questions, and helping enterprises right away sort of stay competitive as quantum computing emerges and starts tackling the computational bottlenecks in those industries. So that's actually all I have today. I'm going to leave it there. I'm very happy. First of all, thank you very much for your attention, and I'm very happy to take any questions you might have.
Hi, I wanted to ask for the case of when you're talking about graph similarity, that's not graph isomorphism?
Yes, graph isomorphism is part of that. It turns out, if you want to get technical, the photon counting distribution of one of these devices after you embed your graph, the two of them are the same for two different graphs if and only if their photon counting distribution is the same. Maybe with some technical caveats there, but that is a graph isomorphism, so that fits within our graph similarity studies. If you're interested in that kind of graph problem, this device is for you. Come hit us offline if you'd like to learn more. Yeah.
Hi. So I have several questions back here.
Oh, hi.
Hi. So for the first one, with your photonic integrated circuit, the one that you brought up on one of the slides, how do you choose which path your photon slash squeeze light state takes? It looked like it was a 1-to-4 splitter.
Yeah, at the lowest level, the gate sequence that you apply can be thought of as a kind of universal programmable linear optical network. And so what you do is the user's data enters by setting different analog voltages across that chip. That changes optical phases that the photons experience. And so that allows you, in sort of the simple incoherent case, you do switching. In the coherent case, you have two squeezers coming in, and you have a 50-50 interaction, then you emerge with an entangled state, a two-mode squeeze state, if you want to get that level. So the routing is done in the sort of the same way that gates are done, and that's based on encoding phases, electronically changing the optical properties. And that's essentially what the user's instructions get compiled down to.
So that brings me... So that brings me to my other question. So in terms of controlling the phases, what are you using? So I'm assuming that you have silicon on silicon dioxide for your chip in terms of the layers. So are you using liquid crystals, for example?
That I probably can't get into publicly. Still kind of our secret sauce. It's a type of phase modulator, and there's a few different ways. We've tried different ways of doing it. I can say it's not liquid crystals, actually. I can say that.
And then my final question is, how do you embed your algorithm onto the chip?
Yeah, it's a good question. I mean, it depends on the application and depends on the algorithm. If you want to do, say, dense subgraph, you have a graph, you have edges, you can represent that as a matrix. mathematically, and that matrix, there's I won't say a simple, but a efficient and straightforward mapping from that matrix into the settings of those phases on the chip. And so you don't have to actually directly set those phases. You can get that graph and use our API to compile that down to the phase encodings that go on there. And then once encoded in the chip, that sets what the interferometric settings are. It sets what the squeezer settings are. As those states are synthesized and pass through these gates, the photon counting on the output, the statistics of those photon counts, of those integer strings that you get for each sample, 100,000 times per second, that's our sampling rate, that will tell you, after some processing, what the, say, most likely candidate for a dense subgraph is. That's kind of how the workflow goes. Yeah.
Hello. Hi. Very nice talk. Thank you. So a layman's question. Everybody today is talking about quantum computing being a specialty market, not mass consumer market. Now, you don't have vacuum chambers. You don't have low temperatures. Lasers can be solid-state devices. What keeps us, in principle, from having this in our iPhones? And if there are no barriers in principle, then can you fantasize in terms of timeline?
If I think I heard the last, can I fantasize in terms of timeline? Absolutely. Yes, it's an excellent question. And indeed, I would say photonics has, in thinking really long-term, really thinking fantasy, it's the only approach. I might get torn down for that, but I'll say it. I think it's the only approach that can be truly solid state. And that means there really are no moving parts. There's no cryogens, there's no gases, there's no pumps, and so on and so on. There's nothing levitating in a vacuum chamber. Now, what's keeping us from having that right now? There is some cryogenics. Those in the know in photonics know photodetectors. The best photodetectors generally need some cooling. And so in our stack, not in the actual computational stage, but in kind of this resource we use for readout, we do have some cryogenics in the game. However, the type of cryogenics that's needed are both much more modest compared to what you need, dilution fridges and so on for superconducting approach. And there is a roadmap, maybe most importantly, there is a roadmap. There's no fundamental reason why we can't get rid of that entirely. So we have some fantasy architectures that we're working on, which are long-term goals to fully go to room temperature and also go fully integrated. So bring the detectors on the chip and also bring those detectors simultaneously to room temperature. So that's not something that's going to happen next year. You'll have, I would say, more limited functionality as that gets rolled out. It won't be able to address all these different applications. But to answer your question, yes, in the long term, you can imagine a core of one of these embedded in a device that you hold in your hand. Absolutely.
Hi. So this graph isomorphism thing that you mentioned,
yes.
Just to pick one of the examples. So you have two distributions that are the same if and only if two graphs are isomorphic. Now, can you actually distinguish those distributions by any efficient algorithm? And if you can't do that, then why do you think this could give you a speed up for graph isomorphism?
That's a good question, and I'm absolutely unqualified to answer it.
Okay.
It's coming from Scott Aronson, so I won't even try. No, that's a very good point. It's a question, can you get statistical significance? Right? And how long does it take to get statistical significance in the presence of noise and imperfections when you're comparing these output distributions? That's something that's absolutely needs to be studied and is being studied. I'll defer you to our algorithms and applications team. I can link you up with them. You may already be linked up with them offline. And also, I'll point you to some of our published research in this area. This applications paper that's coming out hopefully this week, very soon, will be on the archive, and I think it'll go into detail on summarizing graph isomorphism, graph similarity, and those other problems.
Hi.
Hello. First of all, amazing reference to Beatles in your tools.
That's not me, that's our CEO.
So where do you see yourself in the quantum supremacy race, making something applicable?
Yeah, I'm not going to speculate or give any hard timelines. I'll say that the best estimates mean that quantum supremacy would happen. You'd be in that space around that 50+ mark, so 50 to 100, in the same kind of size of qubit count that Google claimed. So on the timeline that I mentioned, that would be early 2021. However, there's going to be caveats, like how much noise, right? If you have a certain amount of noise or a certain amount of imperfections, maybe there is another classical algorithm with the same fidelity, right? That could simulate the distribution. So I think there's a bit more applications, sort of algorithm research on the fundamentals that can go into that problem before I could answer that question. This is not a 10-year plus thing, though. We're now quibbling over single-digit years. I say that as a hardware person, so how long it'll take to get to that point of that size of hardware.